Okay, we're recording. Hello, everyone. We're gonna now today just go over a very simple and quick tutorial. What we're gonna be doing is just combining what we've done in other videos, and it's actually gonna be very very simple, very quick. And yeah, it's like the most basic reinforced agent with that can take discrete actions using a custom environment that we build ourselves. So we're gonna go ahead and just jump right in. We've already been over, how to make the agent and how to make the environment in previous tutorials. We're just gonna do a quick recap and we're gonna play it. And for anyone watching, just know that I'm just taking baby steps through each tutorial. Like each one, it's literally just like the smallest little step, like increasing from the previous. Because I'm trying to just make it very easy. I don't want it to be too confusing jumping from one tutorial to the next. So each tutorial really is a baby step only. Anyways, so we're gonna go over building the environment, and the network, building the network and running the network on the environment to train. Okay, so let's just see what I wrote. All right, so this is an unbatched implementation of reinforce with no reward normalization, advantage, and no entropy bonus. The environment is a simple 6x6 2D grid world, and the objective is for the agent to reach the goal. The agent and the target positions are randomly initialized every episode. The metric being monitored to indicate learning is the average number of steps it takes the agent to reach the goal. So, the agent is still going to be learning to maximize its expected return, expected future reward, discounted sum of rewards or whatever. But the way that we set up our reward function is that you get more reward the fewer steps you take. So, it's going to be navigating the 2D plane and, excuse me. It's going to be navigating a 2D plane, and it's just trying to reach the goal in as few steps as possible. So if it takes the max number of steps to reach the goal, it obviously doesn't know how to solve the problem yet. If it takes very few steps, it knows that, if I'm here and the goal is in this other location, I should take steps along this trajectory or whatever. So let's go over the environment. So this is just a very simple built environment. So it's a class, and we're calling it one target grid world because in future tutorials, when we start using RNNs, we're going to have multiple targets, and we'll discuss that in those other tutorials. So we need to initialize our class, and when we initialize it, we need to define what the state is going to be, and we need to declare a step counter, so we know how many steps we've taken in the environment. So, we're going to have a max number of steps. So we need to keep track of the number of steps we have as well. To create the state, we have a function called init state, initialize state. And it's just going to be sampling several x values and several y values. So we can go ahead and, so it's going to sample 5 random values for our x's and 5 random values for our y's, and this technically only has to sample 2 values for x's and y's, and there is the small possibility that our player and our goal state are initialized in the same position, and that happens sometimes. But anyways, so we have several x's and several y's, and we're just gonna call piece 1, which is gonna be the goal. So let's actually, I do apologize, I'm not trying to take up a bunch of time doing things. Anyways, so we'll call this goal, and that's, we just take an x value and a y value indexed from our list of x's and y's, and we do the same thing for player position. And now we're gonna have XY coordinate for our goal starting state, and then XY position for our player position. And so now we have our player and its goal that it's supposed to reach. So this is going to be our state observation. So we have two lists that each have two elements in them. So what we're going to go ahead and do is we're going to put those into an array, and that array is going to actually be a 2x2 array, and our observation for our environment has to be a one-dimensional vector. So we're going to put those into an NumPy array, and we're going to call flatten on that array just to flatten it out to turn it into the one-dimensional tensor. And we're going to put that all into a list. And this is just putting it into a list for a type conversion, just so things are simpler when we're handling it later. And obviously we're going to return our positions, and that's going to be our state. So now we have a state, after when we initialize. And the reset function for our class is also going to have the same, it's pretty much doing the same thing as when we initialize our environment, because resetting the environment is like pretty much initializing it. So, I mean, there's sometimes, depending on what you're doing, what environment you have, you might have these, like the reset and the initialize function, be slightly different. As you will see, like if we have like, when we use PyBullet in future tutorials to build a custom PyBullet environment. But right here, it's just the same. So now we need a step function to handle, stepping. So, in a 2D plane, there's 4 possible directions you can move: up, down, left, or right. And so there's 4 potential actions. And our observation space, which is, it's not labeled or anything, we know it has 4 elements in it. So our observation space is like 4, and our action space is also 4. So like I've said in other tutorials, based on what you're building, you're going to have to know that on your own, and what the max and min and what correct values and incorrect values could potentially be. And these are all things you have to handle when you're building your own environment. And so with every step we just increment step counter, and we have like a termination condition, like if we've hit like the maximum number of steps we have for an episode. And I just picked an arbitrary value of 15 steps. So if step count is greater than 15, greater than or equal to 15, that's going to be our termination condition for like we've taken the maximum number of steps, reset the episode, and try again. We're going to call self.reset, and the reward is going to be -10. So we're going to give it a large negative reward as compared to what you'll see the other rewards are, if it's a winning condition or just a normal step, like a transition step. So we're going to give it a reward of -10, like, oh, you lost because you took too many steps, huge penalty. And we say playing is false. So in our step episode loop, instead of saying if done, continue, if not done, continue, we're just going to say if playing, continue. So we're saying playing is false because we've reached the end state, and we're going to return our reward, which is -10, and whether or not we're playing, which is false. We're not playing anymore because we've took too many steps. And yeah, so we also need to go ahead and check for like a success condition or a winning condition. And all this is doing is making sure that the X values for our player and for our goal are the same, and the Y values for our player and for our goal are the same. That means our player and our goal are in the same position, and it means our player has correctly navigated to our goal. So that's the success condition. And we have to write out all this logic because we're building our own environment, and we're doing it in like a very simple grid world. But in other tutorials you'll see that you don't have to be so granular with certain things, that if you're using certain packages or certain things, you don't have to specify all these things. Like for example, like in PyBullet, if you were to reach the goal, you could say if 2 objects are touching, and it will just check if the two instances of the 2 objects you're tracking are touching, and if they are. So you could just be like if whatever is touching or whatever, that's your condition, instead of having to be like so granular here. So if we win, we're no longer playing, so playing is equal to false, and we give it a huge positive reward, which is +20, and we call self.reset as well to reset the environment to its starting state. for the next episode, and we return our reward and whether or not we're playing. And this is just how we incorporate our action into updating the state. So, we have values, 4 potential actions to take, and those are going to be 0, 1, 2, 3, or 4, because we're going to be taking categorical actions, so we'll get those actions as integers, and we're kind of just like mapping it, between like what the action is and what it's supposed to do. We're just applying the action to the environment right here. So it shifts the player, up, down, left, or right in that 2D plane. So, like up, we get the Y for our player, and we shift it by, we decrement it by 1. And if we're going right, we increment it by 1. If we're going left, we're shifting it to the left, so we go -1. And the reason why down is positive and up is negative is because I did it the way that you would for like images inside of Python or any other language, where 0, 0 is the top left. And, like if you go over to the right and then down, like that's your, if that makes sense. Like the left and right are the same, but up and down are kind of flipped. Anyways, we don't need to worry about that because we're also not going to visualize in this tutorial. We're just going to be tracking the number of steps it's taking and make sure that it's learning. So this is just a normal step. It's not a winning condition or anything like that. So we're just saying playing is equal to true because we're going to continue playing, and reward is equal to -1 because reward is equal to -1 because we just took a step without reaching our goal state. And the way that you apply all this logic definitely can be different. There's this is not like hard and fast way to do it. There's a lot that you could interpret or change or whatever. And you could put like this logic like after the action, like you take the action and then you check whether it's there yet, and that would be that would actually allot the reward to the correct time step, but you're gonna get the same result regardless. Anyways, so that's our environment. So let's go ahead and hit play to create our environment, and we haven't obviously instantiated it yet, and we don't need that for this tutorial either. We don't. Okay, so we're gonna go ahead, and this code is very similar to the code in the last tutorial. So we're gonna import numpy as np, import tensorflow as tf, import tensorflow probability as tfp, and from tensorflow.keras import layers. Just did that already. Copy and pasting, so you guys know how it is. Import, and we don't need that in this one either. So we're gonna go ahead, do our imports, and then instantiate our environment. So we call constructor. We instantiate our class, and we get returned an environment. And we're gonna go ahead and create our model, which is gonna be our actor. So I think this is the exact same model as the previous tutorial. So our actor just needs to know how many actions we can possibly take inside of the environment and how many hidden units for our hidden layer. And we're only having one hidden layer for this agent or network. So we're going to have a shared layer. Well, we're calling it shared one because I copied this code. But it's only a single dense layer with number of hidden units, and activation function of ReLU. And the output layer is going to be, again, a dense layer with number of action outputs, because we're going to be passing, because this is going to be our logits, and we're going to pass that to a categorical distribution. So now we have our layers, and now we need to define a forward pass in the call function for our network. So we're going to say define call. It takes self and our input observation. And our input observation is a batch of observations. So we call self.shared1, which is our first layer on our input observation. And that gives us x. And we're going to return our output, which we get our output by calling self.actor on the output from our first shared layer. So then we go ahead and instantiate our model. So we're going to say model is equal to actor with number of actions equal to 4 and number of hidden units equal to 256. And the number of hidden units you have is very arbitrary. And for example, in our environment, the way that we're assigning our rewards right now is very arbitrary. And the number of maximum steps and the actual grid size for the plane, potential starting random values. And just realized I do need random because import random. Okay. So yeah, these are, and eventually, hopefully in the channel, I will be able to go over things like reward learning and things like that. Defining good reward functions and stuff like that. But yeah, just remember when you see that this is converging, and like if you try to apply this to a different problem, just know that like I picked a step count so it can converge in not so many episodes, and like I did a little bit of like hand manipulation of the reward so it converges quicker, since we're not using batches either, so that's gonna make it train slower. So anyways, let's go back. So now we have our model, and we need our function to be able to calculate our return for each time step, which we're calling calc g for, g is our return, and it takes a reward trajectory and a gamma. And so we just create an array that creates a discount factor for us, and we're going to multiply that discount factor array to our reward trajectory in order to get the return for one time step. And we have to sum over that so we have a discounting list or array, and we have a reward trajectory or array. And for each time step, we multiply our reward trajectory times our easy discount or our discounting array, and take the sum for all values from that time step to the end, just because I feel like I didn't explain it very well in the last one. So we haven't calculated g's for any time step yet, so we have to define an empty list, and we're gonna take our reward trajectory, which is actually a list, as you'll see right here, and we're gonna convert that into an NumPy array for easier indexing, I believe. Well, actually, indexing would be the same, but type conversion. It's gonna be like, oh, like I wanted a list, but it was an array or whatever. So whenever you see like a type conversion anywhere, it's just so I could get things running. So for every time step in our reward trajectory, so in range length of the reward trajectory, we're gonna take the reward trajectory from that time step on, and that's going to be 2 end rewards, and then we're going to take our discount factor and find out how long this trajectory is, and we're going to take our discounting array, so we can because our discounting array and our reward trajectory array have to be the same length. So we're just going to go ahead and we're pretty much cropping this, or slicing it. So our easy discount has only as many elements as our 2 end rewards, and that's going to be in our equal length discount array, which we're calling eq len discount. And then we're just going to go ahead and multiply those two values. So we know total value is equal to np.multiply our 2 end rewards and our equal length discount. And now I see why I did the type conversion up there. But now we have a trajectory of discounted rewards, but our return is the sum of the discounted of all future discounted rewards. So we have to take the sum of that total value array. And we're going to call that G, and we're going to append. So this is just for a single time step, and it does this for all time steps. So we take our G's, which is our return trajectory, and append the G for that, or the return for that time step. And then once we're done, we're going to return G's. That's a much better explanation than the last video. Anyways, excuse me. So we're also going to have our episode stepping function, where we just collect one episode at a time. And we're going to call environment.reset to reset our environment, even though it should be happening regardless. But just it's very common, just to make sure that when you're starting, that your environment is reset. Just how we declare empty lists at the beginning for our action probabilities list and for our rewards. So we're defining empty list for those, and we're defining plain as true because we barely start to play. So plain is true, and we say while plain continues to be true, perform this loop. So this is just, we're taking our observation from our environment. So to get our observation, we call environment.state, because at no point does our environment return an observation or return a state, but it does have a state, obviously. So I just left it so we can handle it inside of our loop, and for it's convenience for me, but obviously you guys do how you guys like it to. So we reset our environment, and then we take the environment state by calling environment.state, and now we have an individual state from our environment, and our model is going to take a batch of observations or states or whatever as input. So we need to add a batch dimension. So we call tf.expandDims on environment.state along the 0th dimension, and that's our observation that we're going to feed to our model to make predictions and return action logits. So we go ahead and take that observation and give it to our model, and it returns to us our action logits. And that's from what's called an actor critic. So we're not dealing with value yet. So it's going to return a batch of action logits. So since we only gave it a single observation, we're just going to take the 0th output from the model. So we call action logits with the 0th index. And we use that to create a distribution using tfp.distributions.categorical, and it returns to us a discrete distribution. And this is fairly quick. So we take the distribution and we gather a sample for a random action, and that's our selected action index, which is an integer which our environment takes. But this returns it as a TensorFlow tensor. So we're going to get that selected action index and call .numpy to convert it to just a scalar value. So our environment can actually step on it, or use it as an action. So we call environment.step on selected action index.numpy, and our environment for each step, it returns two values: the reward that we received and whether or not we are still playing. And we need to know the action probs, for the algorithm. So we need to call discrete distribution.prob for probability on the selected action that we chose, and that will let us know what the action prob is for that. And we need to append that to our action probs list using action probs list.append action probs. And we received a reward right here when we stepped the action, so we need to append that to our reward trajectory as well. So we're going to do rewards.append reward, and once we've gone through a whole episode, once we've broken out of this while playing true loop, we're going to return our entire action probability list trajectory or array and our rewards array. Okay. So we need a loss to optimize, and that loss just takes our action probabilities and our rewards as arguments, calling that actor loss. So we need to calculate our G's. So we received rewards as an argument, so we call calc_g given our rewards and our gamma of 0.99. Okay, and this is going to return to us a returns array, or a returns array or an array of G's, whatever you'd like to say. And then we need to find our log probabilities of taking any selected action. And in the code up here, I told you guys earlier that we could find log prob of any action. And I don't know why I didn't change that before this tutorial. But you guys can go ahead and try to do that and exclude this line, and you'll be receiving action log probs as an argument instead. But anyways, we're just going to ignore that for now. You guys can go ahead and try that at home. You guys should expect to get similar results, or the same results actually. So we find the action log probs by calling tf.math.log on our action probs, and we have our loss for the loss is going to be the negative sum, the negative log prob, our loss is going to be equal to the negative of the log probs times the returns. And because since since as we're learning, we're going to have trajectories of like different length, we use reduced sum just so we end up with like a single scalar value. And I've seen other people use like reduced mean in some cases, and that's just so our updates of like are of similar magnitude. I don't know how to explain that very well, but you can try reduced mean, and I think reduced mean would be great if you have trajectories with like a high amount of like variance. That way, like the update steps are going to be of like the size of the loss is going to be similar in different like batches or different episodes. But anyways, and then we return that as our actor loss. And then we need to define an optimizer to update our network parameters. So we're going to define an optimizer equal to tf.keras.optimizers.atom, and we're just going to declare our learning rate equal to 0.001. And that's another hyperparameter you might have to tune, and it works great for this problem, or it works decent enough for this problem. Okay, so we're just gonna, so the metric that we're tracking, like we could say, oh yeah, it's gotten more reward over time, and we can just go ahead and like log our reward. But since we used very arbitrary values like 20 and -1 and -10, we can see that it will be learning because it'll be getting increased reward. But for many tasks, the reward is not like, for example, like if it was a pendulum or something. Well, maybe that's not a good example. Well, I don't know of any off the top of my head, but there are many environments where just looking at the reward, it will let you know whether it's learning, but it will not actually let you know like how well it's learning. Like you'll just be like, the reward can essentially be an arbitrary value, and if it's learning, that arbitrary value will go up because it's doing maximization of that, but you won't know how much it's learned in the meantime based on how the reward is assigned. So we're going to be tracking the length of a reward trajectory and using that as a metric. So like if the reward trajectory is using the maximum number of time steps, obviously it's learned nothing. And if it like takes 2 time steps, it's like, oh yeah, it's always like, it knows where to go every single time. So we need to be tracking the length of our reward trajectories. And we're just going to run this for 12,000 episodes. And if you were to implement like batching, you can do it in like significantly fewer episodes, because the gradient updates will be like more in like the direction of like the true gradient or whatever, and right here it's very stochastic, but you'll still get there, you'll still get very close. So this is just normal training. So with tf.gradient tape as tape, we step our episode, taking as arguments our environment and our model, and it returns to us our action probabilities and our rewards, and our loss is going to be equal to what's inside our actual loss function, and that function takes our action probs and our rewards. So then we go ahead and find the gradients of the loss with respect to the model parameters. So we call it tape.gradient loss, and we pass it our loss scalar value and our model.trainable variable so it can calculate the gradients. And we call optimizer.apply gradients, with zip gradients and model.trainable variables to go ahead and actually take a step for us. So our optimizer is going to be taking that step, for it's taking gradient descent, but we have the negative, so it's actually gradient ascent. Anyways, and we're going to go ahead and log our metric or add our metric to our metric tracker, I guess you can say. So we're going to say our average length of our episode, and we're going to add the length of the rewards for this episode. And now we're just going to log this for our own viewing pleasure. So we're going to say for every 50 episodes, we're going to display the episode number, and we're going to display the average number of steps an episode has taken for the last 20 episodes. So, this is going to have a ton of values, and we're just checking the last 20 and taking the average of how many steps. That way, seeing if it's learning or not is much more reliable than just saying average steps to target and printing out the last episode, the last episode length. Taking the average of the last 20 episodes will give you a much truer, letting you know what's actually going on, how much it's learning. Anyways, so I'm going to go ahead and hit run. And it trains very quick because it's each episode is going to be a max of 15 steps. But yeah, so let's go ahead and let this run for a little bit. So just so you guys know, if you're ever doing it and you're wow, it's learning super, super quick. The first step, especially for reinforce, if it looks like it's learning in the beginning, it might be learning a very, very small amount. But a lot of those what you're seeing as learning is just it getting lucky, because it really hasn't had enough experience to learn yet. And a separate thing is if this environment was totally the agent starts in the same place every time and the goal starts in the same place every time, this would train very, very quickly. But that agent wouldn't be able to generalize. And who knows how well this agent can generalize to other environments. But it would do much better than an agent that only learned a single, I always start here and the goal is always here type of situation. So, the other thing is, so you won't really know for this if you set it up the exact same way I did. Usually around 2,000 episodes, you start to see it's decreasing significantly. There's very real signs of learning. But, things like network initialization, unless you're initializing everything to the same random seeds, you can't really expect it to train the same way every single time. And it looks like it's actually in a very bad space right now. Usually it'll be 13 by 1,000 or something like that. So I'm going to let this play, and if not, I'm going to have to go ahead and reset the network and, technically reset everything just so we can see it train if it's not giving us, and yeah, it's giving us 15 for over 20. I'm going to actually just reset runtime. Ooh, that looks so bad. That's not what you want to be seeing. There's zero signs of it learning. It's not even getting lucky at that point. And when if it's learning, like I said, if the number of steps, if the average reward is going down initially, I wouldn't count that as learning. It's just getting lucky. But let's see this time. Let's just wait a minute, and it should be getting down to 5, 6, 7, 8 steps on average after we get to 3,000 to 4,000. And I ran this multiple times before, and in getting ready for for this video. I do know that this agent can learn no problem, especially on this simple 2D environment, 2D plane environment. But if it doesn't learn, go ahead and run it a couple times at home and let me know what hyperparameters you had to tune to be able to get it to learn quicker. And yeah, so let's see. Okay, this is giving some signs of learning. Oh, that 12 looks super nice. And a couple 13s. That looks absolutely exquisite. So you guys can see, as doing something as simple as reinitializing. There's a whole thing of if you have to like initialize it so it starts in a specific space, it's not learning. But like if 9 out of 10 times it works and it's just you happen to like initialize it like with bad starting values, just go ahead and reset. Like these are the algorithms that were given. And look, definite signs of learning. As you guys can see, like average number of steps to reach the target right now is like around like 10. So I'll give it like an extra couple moments, and just so you guys can see that it's continued to hitting lower and lower averages. So yeah, let's just you guys can let this run for 12,000 episodes if you want at home. Try to do batch implementation, and try to do those things that I said this does not include, because I said this is unbatched. This has no reward normalization or advantage or anything like that. These are like pretty similar, and no entropy bonus. And try to incorporate entropy. Like maybe it'll maybe it might help, maybe it might not. Try to incorporate those things. This is good boilerplate, and yeah, it's learning clearly. Oh, 6.9795. Ooh, that looks good. Anyways, tune in, and that's at 2,000 episodes. So tune in some other time. Thank you for watching. Like, comment, subscribe. Let me know what I could do to make these videos better for you guys at home, or if there's specific topics or anything. And it's probably going to be a little while until like the next tutorial comes out. But I will see you guys at some other time. Take care.